So we're going to review using the molarity formula, which is dealing with solutions, something we learned in first year chemistry, and it's really important to us as chemists, so we're going to see this all year long. So if I'm using the molarity formula, we have to use this in moles. It's right in the name. So of course, to get from grams into moles or moles into grams, we need to use the molar mass. And we should remember that adding up the molar mass is just as simple as adding up the atoms in the formula using the masses right off the periodic table. To go from grams into moles, we would take our number of grams and we would end up dividing by the molar mass because we need the grams on the bottom and the moles on the top. If we're going from moles back into grams, say we've completed our reaction and we want to know what we will measure, then we're going to take our number of moles and we'll end up multiplying by the molar mass because we'll need to put the mole on the bottom to cancel and the gram will be on top. What is even more useful for us as chemists, though, is that when we are using small quantities, which we usually are in the lab, we can actually calculate a molar mass in milligrams and millimoles. And in fact, if you look at our example of CH4, if I use this in milligrams per millimole, my molar mass is in fact absolutely still 16.05 milligrams per millimole. I kind of like to look at it as anything over itself, of course, cancels out. So if I have a milli on the top and a milli on the bottom, my number doesn't end up changing. The milli on the top cancels the milli on the bottom. So when I'm working in milligrams and millimoles, my molar mass doesn't change. When I work in grams per moles, obviously my molar mass is going to be the same. That is going to fall out with the molarity formula also. Since that's a ratio, it is exactly the same ratio in moles over liters as it is in millimoles over milliliters. This is symbolized by a capital M. Sometimes you'll hear people refer to it as a particular molar solution, like a 1 molar solution. So mole over liter is a mole per liter. So when you are doing this, you just have to remember you can't mix the streams. It's either in moles, liters, grams, or it's in milliliters, millimoles, milligrams. It's either all millis or no millis. And if you are given grams, because obviously that's how we usually measure a solid in the back in the lab, you have to convert that into moles. Just look at the unit. It's not gramlarity, it's molarity. So here's a quick example of that. If I am given the grams and liters of a solution, let's find the molarity. So I want to find out what the molarity of the solution is when I have 117 grams of sodium chloride in 500 milliliters of solution. So obviously the first problem I see with my problem is that I'm in grams, and it is right there in the unit that I need to be in moles. So I'll use the molar mass, add up 1 sodium and 1 chloride here. I would divide by the molar mass and I'd end up with 2 moles of solute, the solid sodium chloride. But then when I start to set up this problem, I realize I have another problem with my problem. I have milliliters of solution, and if I'm using moles, I have to be using liters. So of course I'll convert those milliliters into liters by remembering that there are 1,000 tiny milliliters in a liter, and so I'll end up with 0.5 liters. Now I can use my 2 moles and my 0.5 liters. If I wanted to work with 500 milliliters, I would have to change that to 2,000 millimoles because I either have to have all of them millis or none of them millis. So in this case, I would take 2 moles divided by 0.5 liters, and I would end up with a 0.4 molar solution. So why do we need molarity anyway? Well, many reactions are done in solution because it greatly increases the rate of the reaction. When something is in solution, it's a liquid and the particles can move easily and they can find each other and collide to have a chemical reaction. But let's imagine a situation. Let's imagine a chemist makes a liter of 0.1 molar sodium chloride. That means that chemist would have to measure out 0.1 moles or 5.84 grams of solid sodium chloride. You would add water to make it dissolve and then top it up to 1 liter of solution. So let's say we make that liter of solution, but for one run of the reaction, we only need 10 milliliters. Well, this solution would have a density very close to that of water. So if the chemist used 10 milliliters of solution, they would have 10 grams of solution. So could we use 10 grams to determine how many moles of sodium chloride we have? That doesn't make any sense. We can't have 10 grams of sodium chloride. We didn't even use 10 grams to make the entire liter of solution. So most of the mass in a solution is really just water. So we can't use the mass of the solution and just divide by the molar mass like we could if we had a pure solid. That means molarity really just acts as a conversion factor between a convenient form of matter, a solution, and a convenient unit for reactions, moles. So let's say a student uses 10 milliliters of a 0.030 molar solution of NaCl. How could we use this to find out how many millimoles we used? Well, it just works like a conversion factor. So I would take 10 milliliters and I would set this up to convert. And it turns out I would end up multiplying, which is a little hard to see right now. But let's remember that big M molarity stands for moles per liter. Wait, I can't cancel a milliliter with a liter. Wait, it also stands for millimoles per milliliter. And now I can see I have a milliliter on the top and a milliliter on the bottom. So it turns out that in that 10 milliliters of solution, I would only be using 0.3 millimoles of sodium chloride, even though that's actually 10 grams of the overall solution. This is a super important relationship for chemists. So I have it on the next slide. The critical relationship here, and I'm seriously telling you, like, write it on the inside front cover of your notebook, tattoo it on your forehead, and look at it every day for the next week. Molarity times volume gets me into some form of moles. If it's molarity and liters, it gets me into moles, and then I can use that to get into grams. If it's molarity and we're working in very small quantities like milliliters, then molarity times milliliters gets me into millimoles, which I can use to get into milligrams. This is just so important. You really need to have this right at your fingertips when we're solving some of these problems. So just to sum everything up here, because I know this video is getting a little long, molarity is a way of relating moles of solute to the volume of the solution. So pretty simply, if I have molarity, if I'm given mass, I have to get into moles. If I have liters, I can do moles divided by liters. If I have milliliters, I can use millimoles divided by milliliters. That will get me the big M molarity, capital M. The critical relationship that we will use all the time is to use molarity as another way to get into moles so that we can do things like stoichiometry. So I can get to moles by using molarity times liters. I can get into millimoles by using molarity times milliliters. And then of course I can use moles to get into grams and millimoles to get into milligrams using the molar mass. If I'm asked to find volume given molarity and mass or moles of a solution, say I know I need 0.5 of a mole to do this reaction to completion, and I need to figure out exactly what volume of solution I would need, then in that case, the volume is going to be moles divided by capital M, or milliliters will be millimoles divided by capital M molarity. You can see that in the triangle there. You can use it by solving the formula, or you can really just use molarity as a conversion factor and cancel out your units on opposite sides of the fraction bar.